we begin our series of reactions now. We're going to start with acid chlorides. Generically, we can call them acid halides, but really we only ever talk about chlorine because the other ones are just very hard to make. So we can make an acid chloride by taking carboxylic acid, which is how we're going to start all of our functional groups, and we're going to treat it with thionyl chloride in the presence of pyridine. Pyridine, as we know, is our chloride abstractor. So, and we're going to end up making our acid chloride. We're going to see that acid chlorides are our most reactive of all the derivatives, and so it's very useful that we can turn a carboxylic acid into one, because then we have a lot more utility, synthetically speaking. Let's take a look at the mechanism for how this chloride comes to be. All right, remember that thionyl chloride. I'm going to just draw it like this. Looks like that. So we have our S double bond O bond, which is nice and electrophilic. We're going to have our double bonded oxygen, the carbonyl, go ahead and attack our sulfur, condensing down to make sure we don't end up with any carbon positives here. In doing so, we end up forming the oxygen-sulfur bond. We're going to have the O minus up here, and then we have two chlorines. So just like with our other carbonyl-based reaction substitutions, we're going to have that sulfonyl come down, kick out one of the chlorines. All right, in doing so, we now have our positively charged nitrogen down here. We have our oxygen, sulfur, double bond OCl. The sulfur business there is a very good leaving group, exceptionally so, because we're going to see it's going to produce a gas once we kick it out. But first we have to deal with this proton that's there. We're going to want to get rid of that. So this is one of the few circumstances we ever use chloride as a base. Chloride is a crappy base, but a protonated carbonyl is a pretty strong acid. So it's okay. We're allowed to do that here. So go ahead, deprotonate. We are then going to form, we're going to lose our HCl. That HCl is going to go and get abstracted by the pyridine. Remember that pyridine has a special affinity for HCl in that it will precipitate it out of solution so that we don't have to deal with it anymore. Because we know that chlorine can be nucleophilic, we don't want to mess with that anymore. So we're left now with our the following molecule. We have our excellent leaving group. We're going to have a second chlorine come along now. It's going to come along and attack as a nucleophile. We're going to go ahead and open this up. Now we have, essentially, we have that OSOCl thing as a leaving group. So that's a Z, right? I'm going to just move our chlorine there. We have our oxygen with the negative charge, and then we have the O sulfur Cl, which now as a leaving group, we're going to go ahead and kick out after we condense down our carbonyl again. And what's actually going to happen here is we're going to form those electrons between the carbon and oxygen, go to form a sulfur-oxygen double bond and kick out the other chlorine. And as a result, we lose SO2 gas. That's the driving force behind this. And we lose that Cl minus ion. So we still have that extra chloride, and we're going to form our acid chloride. So let's take a look at this mechanism one more time so we can go ahead and understand it fully. So we have the first step is our acid, carboxylic acid attacks the sulfur, kicking out a chlorine in the next step. Once we do that, we have a deprotonation of our protonated carbonyl. We produce HCl, which goes ahead and reacts with our pyridine. Another chloride comes around, attacks our carbonyl, opens it up. We have that tetrahedral intermediate, which then closes down, kicking out our fancy SO2-based leaving group, producing that sulfur dioxide gas, which bubbles away. So again, that's our driving force. Le Chatelier's principle says if you remove a product, the SO2, you'll drive the reaction towards the product side. And so we end up with our acid chloride. And we're going to see that these do many, many, many things. And so I used an acid chloride in our kind of general mechanistic examples, but we're going to see that they're so reactive that we don't really need to have catalysts there. We don't need bases or acids when we're hydrolyzing acid chlorides. They're very, very reactive. We can just use water to remove them. All that work to just remove it, I mean, we could. But generally, it's not something we try to do. Just in the presence of water, you'll end up with a carboxylic acid again. So these need to be stored very carefully in waterproof conditions, what are called dry conditions. No water around. You have to have special little things that absorb water, like desiccants, there to protect it, because these are very reactive. And so we're going to want to protect them from water at all costs, because they will very readily react. In the next video, since this is a good place to kind of pause here, we'll take a look at what acid chlorides actually do in terms of reactions.